Okay, our next example in Bernoulli's equation is a pipe where the diameter changes. And so here we have a pipe where the water is flowing at 4 meters per second, then the diameter doubles to 10 centimeters, and so the velocity decreases, and so what would be the resulting pressure at that point? So let's write down Bernoulli's equation. So we have P at 1, that's pressure at 1, plus rho GH at 1, plus 1/2 rho V1 squared is equal to the pressure at point 2 plus rho GH at point 2 plus 1/2 rho V2 squared. Well, the first thing we need to do is figure out what the velocity is at point 2. If the diameter doubled, what does that do to the cross-sectional area? Well, if we say that this is A1, the cross-sectional area 1, and over here this is cross-sectional area A2, we can see that A2 is equal to A1 times the ratio of D2 over D1 squared. All right, then if D2 is twice as big as D1, we can then say that this is equal to A1 times, let's say here, times 10 squared over 5 squared. That would be 100 over 25, or 4 times A1. So we can see by doubling the diameter of the pipe, we quadruple the cross-sectional area. And because we could say that A1V1 is equal to A2V2, that then implies that V2 is equal to V1 times A1 over A2. Now, since A2 is 4 times as big as A1, so we can say this is equal to V1 times A1 divided by 4 times A1. This cancels out, and so now we can see that V2 is 1/4 of V1. So if V1 is 4 meters per second, then V2 has to be 1/4 of that, or 1 meter per second. All right, so now that we know that, we're now ready to tackle Bernoulli's equation. First of all, the height doesn't change, which means that the term rho GH1 and the term rho GH2 has to be exactly the same. They stay constant. So I can go ahead and divide or just simply remove it from both sides of the equation, which now means the equation then simplifies to P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. So since I'm looking for P2, that's ultimately what I'm after right here, I can then solve this equation for P2. I can move the 1/2 rho V2 squared to the other side and flip the equation around. So now I end up with P2 is equal to P1 plus 1/2 rho V1 squared minus 1/2 rho V2 squared. All right, now I think I'm ready to plug in some numbers. First of all, P1 was 2 atmospheres, so we can leave that there. Or before I do that, you know what? I think I'll factor out a 1/2 rho. That makes it a little bit easier. So P2 is equal to P1 plus 1/2 times rho times V1 squared minus V2 squared. That makes it a little bit easier to work with. So let's move over here. Plug in P2 is equal to P1, which is 2 atmospheres. We don't have to convert that to pascals. That is fine. Plus 1/2 times the density, assuming that this is water. The density of water is 1,000 kilograms per cubic meter. And then I multiply that times V1 squared minus V2 squared. Now remember, V1 squared was 4 meters per second. So that's 4 meters per second. We have to square that minus V2, which was only 1 meter per second. So that's 1 meter per second. And we have to square that. So it would be 16 minus 1, or 15. So we have P2 is equal to 2 atmospheres. 1/2 of 1,000, that would be plus 500 kilograms meters cubed. And multiply that times 16 minus 1, or 15. That would be meters squared per second squared. All right. Now, looking at the units. Is kilograms per cubic meter times meters squared per second squared. Is that pascals? I don't know. Let's find out. Well, first of all, this cancels out with 2 of those. So now we have kilograms per meter per second square but I need pascals. I need a unit of pressure, which is newtons per square meter, and a newton is a kilogram meters per second squared. So it looks like I do need a meter here, and I do need another meter over here. So that means kilograms meters per second squared divided by meters squared, which is indeed Pascal. So units work out. All right, so what's 10 times 15 times 500? So pressure 2 is equal to 2 atmospheres plus, that's interesting. If the velocity slows down, it indicates that the pressure goes up. Does that make sense? Well, let's find out here. So here we have, if the velocity becomes smaller, well, if this becomes a smaller quantity, then something else has to get bigger. So this becomes smaller, that means this has to become bigger, which is indeed what we're finding. So with Bernoulli's equation, we can see, first of all, when the height goes up, pressure goes down. But when the velocity goes down, pressure goes up. So go ahead, we'll continue here. So this would be 7,500 newtons per square meter. And of course, we want to convert that to atmospheres, and the conversion from atmospheres to pascals or pascals to atmospheres, right here we can say that 1 atmosphere is equal to 101,300 newtons per square meter. So this is actually a rather small fraction of an atmosphere. What we have to do is divide this by 101,300 newtons per square meter to convert to pascals. So let's do that. So we have 7,500 divided by 101,300 equals, and so we get this is equal to 2 atmospheres plus 0.074 atmospheres. And so the increase in pressure would be 2.074 atmospheres. There we go. That would be the pressure at point 2. A slight increase of atmospheric pressure due to the slowdown of the fluid in the wider section of the pipe. And that's how you work a problem like that.